to give you a demo on a couple of the different 9-axis or 9 degree of freedom motion sensors that we have in the makerspace. We've used the accelerometer that's built into the circuit playground to get approximation of angle that something is rotated at. That works because the accelerometer is always measuring gravity, a downward pull towards Earth. And so if we tilt something in an axis, we can get a sense of whether it's going to the left or the right or front or back, etc. That's a very kind of crude way to measure the orientation of something, because if that object is then moving or accelerating in any direction, it's going to throw our understanding of that data off. Further, if we want to know the compass orientation of something, doesn't help us at all with that. So I've got two different sensors here. This is the IMC. Will this make it bigger? Nope. The IMC 2948. You might be able to see that. And this is the BNO 055. They look quite similar in size and shape. They both use this adafruit stemma quick connector mechanism, and they're both adafruit products. I've talked about this in other videos, but very briefly, you want to connect ground to ground, power to 3.3 volts, and then the blue is SDA and the yellow is SCL. These are the two data lines. I find it's helpful to write on the clips here, SCL and SDA, just so you remember which is which if you're taking this apart and putting it back together several times. So 9 degrees of freedom, what does it mean? These sensors have an accelerometer. They also have a gyroscope and a magnetometer. So the accelerometer is the same as what's in the circuit playground. The gyro, however, measures spin or tilt, but not in the sense that I could tell that this is tilted at 45 degrees. It measures the tilt while it's happening. So it's measuring or spin while it's happening. So once the device stops moving, the gyroscope settles down. But while it's in that kind of rotation, we can measure that. And the magnetometer measures XYZ of the electromagnetic field around the sensor. So in a sense, that will be able to give us magnetic north, but it is also susceptible to magnets that are in the environment, like speakers or rare earth magnets that might be part of your project, or large metal objects even. So that's something to be aware of. With those three sets of 3 axes combined, we can finally determine the location of this object and orientation of it in space. Now, the issue with that is, even though those 3 sensors are on this board, they need to be calibrated in reference to each other every time the device is powered on. That itself is a bit of a process that typically involves running a certain sketch on your Arduino, generating the calibration matrices for the sensor, saving that as a spreadsheet or a text file, and then uploading that into non-volatile memory like EEPROM on the Arduino, So it always has access to that calibration file, and then you can use the sensor. That in itself is a complex process. And then even then to generate the math that takes the accel, the gyro, and the mag and turns it into a yaw, a pitch, and a roll um, is not casual at all. Let me see if I can find this example. Yeah, so just as a little example, the problem is that like you can get the data, the 9-axis data, but you need to give it like a reference, like how it, or that calibration, right? So when it's uncalibrated, it's just going to be very chaotic. You can get it calibrated, but then you need to make it referenced to like the world that it's in, so it can be off axis. And then once you do that, you can see like how this object relates to space. This uses a lot of trigonometry and matrix math, which I am not going to get into. Thankfully, this is why we have libraries, or this is where libraries become very helpful. So I'm just gonna show little samples of each of these and the libraries that go with them. There are other sensors out there too. There's a couple LSM 9-axis sensors that work too, but I'm going to talk about these two in particular and why. So this IMC chip, to get the raw data off of it was pretty trivial, but the raw data doesn't necessarily help us. Both of these chips have a digital motion processor built into them, so they perform the calibration and all of the trigonometry and matrix math in the chip itself, which is great. So the issue with the IMC one historically was because that math is so complex. It was proprietary, and they weren't letting anyone use it, even though it was there. They've recently changed their mind about that. Unfortunately, at this moment, the Adafruit library has not been updated to account for that, but the sparkfun library for this sensor has, and the sparkfun library works with this device. So let's take a look at an example. So if we go to sparkfun, 9-degree freedom, IMU breakout for the ICM 2948, and we look at Arduino, and I'm going to look at the Quat9 orientation. Or do I want the Quat6 Euler angles? I might want the Euler angles. Let me see. Nope. I want the this one, the orientation. So there's two ways we can think about the object in 3D space. One is with Euler angles, and one is with orientation, the yaw, pitch, and roll. Both work. The data just works a little differently. Um, Let me back up. One of the things that we need to do, though, to get this to work the way we want to is if we look at the comment at the top here, I was just talking about the digital motion processing. We need to edit the library to allow that again, because here we have the InventSense confidential application of program sequence for DNP hardware functions. So if we want to take advantage of all that stuff that they've started to share, we need to turn it on. And it tells you exactly how to do that in here, but I'll just show you. I'm going to go find the library file. And if I go into my Arduino folder and look at the libraries, then I can find the sparkfun 9-degree freedom, and if I look in SRC utilities, I can find that file that they're talking about, .h. And I'm going to open that with Atom. And they said line 29, which is right here. So I've already uncommented that line. You might see it like that. Just take rid of the slashes and save it. And then you might need to restart Arduino to enable that proprietary processing. Then looking at the example, a lot of this will be abstract. Unfortunately, there's some bonus stuff in here that we don't need, but you want to pay attention to that. So there's a lot of these if and def expressions for quant animation. So if you wanted to use did they talk about that? Quant, yeah. So if you uncomment this line, you can use Zane's Node.js tool found there to, I'm guessing, visualize the object. You can also uncomment this one to use SPI. We're not going to use that. We're using the StemmaQuick I2C. So we're going to leave that commented. We're going to leave that commented. Where you're going to transfer this over to your own code, what that means is that all of these statements about quant animation, you can take out anything referencing SPI, you can take out, but you need to leave the else conditions, right? Because we are the else state. Not using that and not using SPI is the else, so we want to keep the else. This is telling it to start the I2C. And then we're going to initialize the processing. We're going to check if we are getting the data we expect, reading it, and then oh, did I actually want the other one? Well, anyway, let's upload this and see. And I'm going to switch my sense here because I've got the BNO one plugged in. And we'll update this. And look at the serial monitor. Yeah, so yeah, I got the files mixed up. Sorry. So this is giving me the Q1, the Q2, and the Q3, which are, I believe, values -1 to 1 for the object in space. Let me upload the other file because it's a little easier to understand. This data is ultimately more reliable, but for demonstration purposes. So yeah, Euler angles. Okay. And so one thing I've noticed is that with these demos, you just need to like, I think because of the other stuff they're doing, you need to activate the serial port. So I just enter anything to get it kind of started. And now we can see the roll, the pitch, and the yaw. Okay, so if we have an object, pitch is going to be if we think of ourselves as an airplane, pitch is like tilt up and down the nose of the plane. Roll is tilt left, right, like the wings of the plane tilting. And yaw is like our compass orientation. The problem sometimes people have with these Euler orientations or angles is that the yaw will hit a certain point and like reset itself kind of, or like lose its sense of completeness of the circle that it's rotating in. So that's just something to be aware of and to check with your setup in your application. Okay, so let me look just so we can see where that's coming from. So you can see that they are taking the Q1, 2, and 3 from the other application, and they are just doing some more trigonometry to develop the Euler angles. There we go. Okay. So that's the one option. This sensor is much improved now that InventSense has made that DMP processing available. Before in that sparkfun has put it into their library. Before that, these sensors were actually very hard to use, and I would recommend something else. But like I said, now that we have that processing available, these are okay. The other one, the BNO 055, I want to show you that one too. The benefit of this one, it just has a few more features. You can look at the Adafruit page to see what those are. It's always made its processing available, which is great. The difference is that this sensor is about twice as expensive as this one. So you pay for the Extra features. So this one we're going to do the adafruit library. So adafruit BNO 55, and we'll just look at the sensor API first. Either of these libraries, I think you're going to have to download several other libraries, so just be aware of that. This one has some helper functions. There's less superfluous stuff here, which is great. I think everything's related to our sensor. This is in the setup, we're just basically turning it on, calling two of those helper functions. And then in our loop, we're creating an event object, getting an event from the library to that object, and then looking at that event to get our X, Y, and Z orientation. They're calling it X, Y, and Z here. It is still yaw, pitch, and roll, but I think they're in a bit of a different order. So pitch is Z, roll is Y, and yaw is X. And then this another helper function is displaying the calibration. Like I said, this one self-calibrates, which is fantastic. So again, all of this has been very abstract, but I want to show you one more thing which helps visualize what all this is about. This example works with this website that only works in Google Chrome. And hopefully I can get it to connect. Nope. Let me try. Plug and unplug. I swear I had this working. Okay, yeah. What it's requesting serial data from the Circuit Playground, and Arduino is sometimes very possessive of the serial ports, and you can only have one thing on a serial port at a time. So quitting Arduino will let other things see the serial port that the Circuit Playground's on. But now, as you can see, when I rotate the sensor around, I can rotate the bunny rabbit. So this is the level of object precision that we have with this unified or fused sensor data, looking at all 9 axes at the same time and turning them into an orientation of an object in space. You can't do this without those 9 axes of information, the accelerometer, the gyro, and the magnetometer. So if you want to really know, like, how is something oriented in space, um, you need to use a sensor like one of these 9 degree of freedom sensors. As you can see, it's giving us the serial port information, and then it's also showing us its calibration status over here as it tries to self-calibrate. There you go. So those are two of the different sensors that we have in the makerspace and how you might start to approach using them on your project.